Please welcome to the stage Mr. Eric Anderson.
Thank you very much. It's great to be here. We're going to have a nice discussion. I will make sure to leave time for questions at the end so we can talk about some of the things that you'd like to learn. What I'm going to go through today is an overview of Planetary Resources, the vision behind the company, what our plan is, and what I suppose some recent updates have been. So hopefully you'll get a better idea of all the things that are going on. It's been very, very busy since our launch. And for those of you who were at the National Space Society meeting, this presentation is similar, but there's a few different things. So I think it's useful for all of us here in the industry to kind of get the whole picture, and there's some fun parts in here too. So let me jump in, and then I'll make sure to leave lots of time for questions at the end. Okay, so you hit it right on the head. The reason we're doing this is because it's inevitable for humanity's future that the resources of the solar system need to be brought into our economic sphere of influence if we want to have a future that is on a forward trajectory and has the prosperity and the increases in prosperity that recent generations have enjoyed. The fact of the matter is that the population of the planet has grown a lot over the last couple hundred years, and people live longer, people live much better lives. It's really an extraordinary time to be alive, and yet we're just at the cusp of doing even some of the more incredibly exciting things that we never thought were possible before, or we thought would be hundreds of years away, like having people going and living on Mars and visiting the moons of Jupiter and things like that. And in order to really do that part of it in mass, to have not 10 or 20 people go to Mars, but millions of people go to Mars, there's no question in my mind that we need to make use of the resources in space. Similarly, as you look forward in terms of the Earth and the natural resources that the Earth has, you would be frightened if you really looked at element by element and substance by substance what we have to work with over the next 100 years, for example. It's not a great story. We've used a lot of what's easily accessible on this planet. I'm not just talking about fossil fuels. I'm talking about other elements, very, very, very valuable elements that are very much a part of our technological lives and industrial processes, critical for, again, ensuring a future of prosperity. So I also have no question in my mind that at some point in the future, resources from space will play a big role on Earth. And for that reason, for those two reasons, Peter Diamandis, who's my co-founder, and myself decided that it was time to begin the extremely difficult task, yet extremely rewarding task, of beginning to bring the resources of space into our economic sphere of influence. And that is the reason Planetary Resources exists. And as a longtime Space Frontier Foundation advocate, I know that's definitely part of what we're trying to do here at SFF, so it's doubly exciting to be here today to talk about that. Okay, so as I said, if you believe that if you want humanity to have a great future over the next few decades and centuries, then it will inevitably lead you to the conclusion that we need to make use of resources in space. And if you believe that we need to make use of resources in space, it will inevitably lead you to the conclusion that the near-Earth asteroids, in particular, are very valuable resources that we need to be able to harness to power that future. The near-Earth asteroids, in particular, and I'll show you a couple slides on this, are extremely easily accessible, and they're filled with all sorts of materials and substances and elements and just the kinds of things that we need to better explore space, to reduce the costs, and to ensure that lots of things that are really expensive now on Earth come down in price by orders of magnitude in the future. So we launched the company on April 24th as a Peter Diamandis and myself, we've known each other for almost 20 years, and we really were thinking back in 2007, 2008. We had co-founded Space Adventures together and started to kick off commercial human spaceflight. We've had, put a few flights under our belt and continued to work on that. And we were really thinking sort of on a brainstorming day, what's next in space? And asteroid mining and mining in space is nothing new. Science fiction authors have been talking about it for decades, and people certainly have thought about it before. But I guess we really kind of drew it out and decided that now was really just the earliest time that it would start to make sense. The confluence of the reduction in launch costs coming from companies like SpaceX, the reduced cost of building spacecraft, the information technology advances that we have, and frankly, the fact that humanity is becoming more and more aware of the fact that we live in a resource-constrained planet. All those drivers together really made it apparent that starting a company to mine asteroids and go to space was time for that. And of course, everybody, people who we talked to at first were asking us how many decades it would take us to do that, and gee, would that happen in the far future? And as we started to explain the details, they became really aware and believed that this is not something that's going to take decades. It will take a while. It's certainly going to have risk. There are certainly going to be times when we fail and we have to pick up and start again. But this is going to happen sooner than people think. And the confluence of the commercial spaceflight industry, and when you have people like my friend Elon Musk, who's everybody knows here, talking about potentially going to Mars in the next 20 years, and really meaning it, and I believe him. We're going to need resources to help drive that exploration. So it's not just a few dozen people, but it's millions of people. So this is very real. It's totally something that I think is. I hope we have lots of competitors out there. It's something that I think is really, really important for the future. It's right up the alley of the Space Frontier Foundation. And anyway, so when we founded the company 2 or 3 years ago, we decided to launch the company in a press conference in Seattle on April 24th, and my expectation, because of the fact that we have some pretty big name investors and it's a pretty cool idea, was that we would get a fair amount of press, but even my expectation was significantly exceeded by the amount of press that was out there, and really struck a nerve. We hit a nerve with the public. People just said, wow, this is the kind of future I want to be part of. I'm glad I'm alive today. I'm glad I'm alive today, and good on you. And I thought, I was a little bit afraid that some of the non-space advocate type people out there would say, oh, this is, we've destroyed the Earth, now we're going to go rip up space, it's terrible. And that didn't come. There was a little bit of that, but most of it was very, very positive. And so that was a big, big step. I've got to show you the Jon Stewart treatment on Planetary Resources. So if you have not seen it, even if you have, it's great. The best part about it for me was that I didn't actually know that we were on there until the afternoon of the next day, and someone came by and said, hey, that was really great last night on Jon Stewart's show. And I was like, what? I was so busy thinking, working on something else and just following up with everything. And so, you've made it when Jon Stewart makes fun of you for 8 minutes on national TV. So it's worth watching. Let's watch it right now. Whoops. Hang on. Whoops.
Roll 212! This may seem like science fiction, but today a group of space pioneers announced plans to mine asteroids for precious minerals.
Space pioneers going to mine asteroids for precious materials! Boom, boom! Yes! Stu Beef is all in! Do you know how rarely the news in 2012 looks and sounds how you thought news would look and sound in 2012? The best part, didn't know government boondoggle. This asteroid retrieval project is being completely handled by eccentric billionaires.
They are some of the most influential and wealthiest men on the planet. Google's Larry Page and Eric Schmidt, director James Cameron, X-Prize founder Peter Diamandis, and billionaire Ross Perot Jr.
If you put two Google billionaires with a Microsoft billionaires and some astronauts together, you can't go wrong.
That's great. I think, let me see, we have a little bit more here. I think that might be it, but hold on. Yeah, let's just wrap it up on this part.
I love this story, but it seems... I love this story. But let's face facts, it seems a little far-fetched. That's why it's a perfect candidate for our brand new segment, Bullshit or No Bullshit, with astrophysicist Neil deGrasse Tyson. Let's put 60 seconds up on the clock.
Good evening, John.
Dr. Tyson.
Good evening.
Dr. Tyson, tonight's question.
Yeah.
Asteroid mining. Bull or no bull?
John, in this case, the answer is no bull.
Amazing.
And John, you know, your opening credits still show the Earth rotating the wrong direction. I'm just saying.
So that's really great. I love that one. Okay, so again, just some summary after the announcement. You know, within just a couple weeks, we had just been deluged by people, job applications coming in. We're still getting literally hundreds of job applications per month. As a result of that, 5,000 people or more actually took the time to send a custom email about how we've changed their life and they're going to study science now and all this kind of stuff. It was really, really, really inspiring for me personally. You know, more than 2,000 people wrote us and said, we want to invest in your company. How do we do that? You know, coming from the early days of the commercial space industry where raising money was not that easy, the early days of Space Adventures, for example, where it was really tough to raise money, and we just had to figure out stuff to sell in order to survive rather than just raise money all the time. You know, this company, it's been a lot easier. There's, you know, most of the people we've talked to just say, yeah, I'd like to invest, or people, you know, saying, one email was great. I should have showed it up here actually with blank the name out, but some guy just said, look, I really want to give you money. Just send me your wire transfer details. For real. And so we're like, okay. So anyway, we're really growing that community. We're going to be very much active with our base of supporters, and we're going to do frequent press conferences or announcements or updates online and in person and things like that as we begin to do more stuff. So some of these quotes are great. These are just random folks who've written in. I like the one right here in the middle. I'm tearfully joyous that this company now exists. I felt that a resource-strapped humanity will always look forward and drive global conflict. Thanks to you, humanity has an outward-looking hope, which is great. And, you know, it's just been really an honor to be the subject of so much positive enthusiasm for something that we all in this room certainly have been wanting to see for a long time. So that's great. So let's go back to some of the technical stuff. Where I left off before we started talking about the announcement was that if you believe resources in space are important, inevitably the roads will lead you to the fact that the near-Earth asteroids are vital. And so just to put some perspective on that, I'm not going to read through every one of these facts, but I'll just point out a couple. You know, we only knew of a couple near-Earth asteroids until 10 or 15 years ago. And now we know of approaching 10,000. Okay, these near-Earth asteroids are not in the asteroid belt. They're asteroids that are of 3 or 4 different subtypes that I'll show you in a minute, and they approach Earth. They are close to us energetically. They're hanging out in the inner solar system right now. They also happen to be the ones that could be dangerous to us if we're not careful. But as a matter of fact, there are 10,000 of these near-Earth asteroids, and that represents only 1% of the known asteroids represent only 1% of the expected population, which is somewhere near 1 million. if you draw the dividing line between what's an asteroid and what's just a, maybe say that the minimum has to be 5 meters or something like that, you might come down to 500,000, but somewhere between 500,000 and 1 million near-Earth asteroids exist, and we only know of 10,000 of them. So we just started to figure out where these things are just recently. So we're going to find out just how many there are over the next few decades and just how useful they can be. I sort of equate it to, because they're not in a gravitational well, it's kind of like fossil fuels. We were lucky as humanity because we got to start our industrial and technology revolution over the last couple hundred years powered by really easily accessible fuel, energy. And, that's going to run out someday. But we've been able to do things like go to the moon and develop artificial intelligence and computers and all this stuff because we have really cheap energy. And I sort of see the near-Earth asteroids as the same way. If you were to calculate the total energy, if you will, or the potential energy and the energy in the materials of the near-Earth asteroids, you would find that it is extremely important to be able to utilize that energy to explore the solar system. And so if those near-Earth asteroids weren't there, it'd be a lot harder for us. We'd have to bring everything from the surface of the Earth. And bringing everything from the surface of the Earth to send millions of people to Mars would be really tough. It'd be really tough. So the near-Earth asteroids are really, really important. What's also interesting is just to compare, just to show you how they relate to something that we all know about and talk about as the moon, which is a great subject of exploration and something I'd love to see explored as well. 17% of the known near-Earth asteroids are actually easier to reach than the surface of the moon. And that's because, of course, when you go to the moon, you have to slow down. And when you go to an asteroid, you don't land on it, you dock with it. So these are essentially rocks in space that you dock with. You can go back and forth from with very small energy. And that's very, very useful. Okay, just to give you an idea of scope, the second to last bullet is great. We're not talking also about monster asteroids to be useful. Anything that's a few hundred meters across, okay, down from, say, 100 meters up to 1 kilometer, any of those are really, really useful. If you find one that's carbonaceous, like I'll show you, it's got millions of pounds of potential rocket fuel on it. If you find one that's high in platinum group metals, it's got more platinum group metals than have been mined in the history of humanity. If we were to stack up all of the platinum group metals, all of them that have been mined in the entire history of humanity, they would fit on probably half this stage and stacked up maybe about that high. And these are platinum group metals that are critical for things like catalytic converters, medical devices, components. They're really good. They're really good components, actually. They have great conductive properties, and we just can't use them that often because they're ridiculously expensive, $1,500 an ounce on average. So these are really interesting targets, and they've got a lot of really good stuff on them. So let's talk a little bit more about that. So there are 4 key types of near-Earth asteroids. Won't go through these here. You can look it up on Wikipedia. But about half of them are Apollo asteroids. So their orbit is a little bit longer than a year. Their semi-major axis is a little bit longer than 1 AU. But they sort of hang around in the inner solar system. By the way, another really interesting fact, the average lifetime of a near-Earth asteroid in the inner solar system is about 30 million years. So they don't hang around for long, actually, on scales of solar system. They either get swallowed up by the sun or smack into one of the inner planets, or they get ejected somehow and flung out of, way into deep space. So we're not going to miss them. We need to use them while we have the chance to do so. And of course, they are replenished by other comets and things coming through. But it's a really interesting and very dynamic process, what goes on in the inner solar system with these near-Earth asteroids. So here's a graph that just shows you the numbers, at least the numbers of the ones that we now know. And this is actually a time series integration. So the number of these dots is increasing with time, and we're probably at 2008 now or something like that. But just in the last few years, we started to discover near-Earth asteroids at a geometric rate. This was back at the beginning. And it's just fascinating. I mean, we're now at 10,000. You know, next year will probably be 11,000, 12,000, 14,000, you know, blah, blah, blah. And that, of course, doesn't even count the ones that we're going to discover by going up and putting our own space telescopes in orbit, or if somebody like the B612 Foundation gets to launch their Sentinel, and then we can discover 90% of them. So this is really important to do that, and they're just great targets for resource extraction. Okay, so this is what I call the MasterCard slide, just to give you an idea of how valuable asteroids are. So just the data on them is, of course, very valuable for scientific purposes, and that's kind of the first line. So right now, in today's world, today, we spend around the world, across all the space agencies, a few $100 million a year, let's say, some number of hundreds of millions of dollars a year pursuing asteroid data, and that sort of takes a 5 or 10 year time scale and averages it out and things like that. So just the data is worth something. People like that. People like getting data. Scientists like data. We can learn a lot from these things. They're remnants of the inner solar system. Of course, once we get to the point of being able to extract resources from them, you can now add 3 zeros to the marketplace, and now you're talking about hundreds of billions of dollars. Okay, the resource and energy industry literally drives growth for humanity. So being able to add hundreds of billions of dollars of potential resource from space for use in space or for use eventually back on Earth, I think obviously is a game changer for humanity and really can help drive prosperity. But we're talking hundreds of billions of dollars in the marketplace. And the reason I call this the MasterCard slide is because the last one you can't put a price on, which is we have, we have a Tunguska class event every few hundred years, okay? And for those of you who don't know, Tunguska is a region of Siberia that was just absolutely smashed by an asteroid in the early 1900s. I think it was 1908, 1907 or 1908. And had that strike occurred in really, most other places on Earth, it would have killed lots and lots of people. If it would have hit the water, it would have caused a tsunami. If it would have hit a populated area, you know what would happen. So it just so happened that it was in the middle of Siberia, and it flattened trees for literally hundreds of square miles. And this is an asteroid that's only 30 meters, 40 meters, something like that. So this happens. The time constant for these things happening is hundreds of years. I mean, there could be one by the end of the century. There could be one in a few decades. We may wait a while, but we don't even know because we don't know all of the asteroids yet that are 100 meters or less. We don't even have, there's probably 60 or 70% of them that we have not found yet. A lot of the bigger ones we have found, but not the smaller ones that can still be quite damaging to locations. And so how do you put a price on that? The capability of moving asteroids around is obviously a really important thing for humanity to have. So that capability we will provide for humanity as well, at least companies like us and in the industry over the next few decades. All right, so just to give you an example as well, it's not just barren, it's not just metallic rock or sort of homogeneous with one element. These particular kinds of asteroids, the carbonaceous ones, have a lot of good stuff on them. And a lot of the asteroids are carbonaceous. So you've got, in some of these, up to 20% ice, liquid water as ice. Now, we all know we can break down liquid water into its constituent parts and make rocket fuel. But there's other stuff on there as well. There's methane ice, not in as great of quantities, but of course methane is natural gas. That's a pretty nice thing to have, especially if you want to go to Mars. You want to be able to have engines that use methane, and then you can manufacture methane on the Martian surface. And then all the metals. You've got the platinum group metals, which also exist in these carbonaceous chondrites. And so the platinum group metals for some of these asteroids are a couple orders of magnitude better in concentration than they are in the best platinum mines on Earth. So for those of you who heard me talk before, you probably heard my joke, which is, hey, Planetary Resources, well, we've been mining asteroids for centuries. We have, actually, because the sites of asteroid impact on the Earth's surface are the only place where you can find platinum group metals. They do not occur anywhere in the Earth's surface. That's because at the very beginning of the formation of the planet, all the really heavy stuff, all those ferrous materials and the ones that, like iron, have high atomic numbers, they just sink to the core. So we got lots of platinum here, but it's all in the core. That's not that easy to get to, okay? So I don't think we're ever going to do that. But the fact of the matter is that the platinum and the platinum group metals that we do get are actually mined places in South Africa, Canada, from sites of previous asteroid impact. And then a really good mine might have a part per billion So it's really expensive to refine it. That's why it's $1,500 an ounce. Okay, so here's just a smattering of some of the materials on there. Lots of good stuff: hydrogen, oxygen, carbon, iron, nickel, cobalt. Those are great. And then the platinum group metals: platinum, palladium, rubidium, rhodium, iridium, rubidium, and osmium. All the good stuff. Okay, so here's what we're going to do. So this is the Planetary Resources plan. The most important thing to do first, we've decided, is to create a series of orbital propellant, let's just say propellant depots spaced at proper locations throughout the cislunar, the Earth-Moon system, and then ultimately in the inner solar system. We're trying to figure out, and so figuring out where those should be and where would be the optimal will be driven by what's happening over the next couple of decades. Is NASA a customer? Will NASA be going to Mars or to asteroids? Will private industry be going to Mars or the moon or somewhere else? And so we will, though, be the capability that enables deep space exploration once you get out of LEO to be significantly less expensive than it is now, because you don't have to bring all the fuel that you're going to need to go that last half of the way energetically from the surface of the Earth. So the calculations here, if you actually work the math, you're talking about a payload amplification factor, if you will, a mass multiplier in terms of what you can do of somewhere between 10 and 20. So that means you can drop the cost of deep space exploration by at least an order of magnitude and maybe 20. That's a game changer. Again, couple that with reduction in launch costs due to reusable vehicles here on Earth. We're talking about a really viable way to think about going out into the solar system for just a fraction of what it takes now. And the real key is that these asteroids have on them the volatile materials that are required to create the fuels. So we don't have to bring any of that stuff with us. Okay, we have a wonderful power source in the inner solar system. It's a great fusion reactor 93 million miles away from us that puts out 1.366 kilowatts per meter squared. And you get that 24 hours a day, 365 days a year in space. And with a pretty manageable sized mirror, you can generate megawatts of power easily. And with high temperature electrolysis, you can convert ice into its constituent hydrogen and oxygen with about a 65% efficiency. So it's, of course it's hard. It's really hard. We have to solve lots of problems. But this is the way we can build orbital and beyond depots in the inner solar system to really allow that future that all of us want. And so we're going to do that first, okay? Now, we've talked a lot about platinum group metals, lots of other great materials out there. All of that is enabled by having the energy. Once you've got fuel depots out there, you can move stuff around easily and far less expensively. So we really feel that that's the first step. Now, NASA has had on its technology roadmap this idea of fuel depots for some time, which is great. But of course, they're thinking that we should just bring fuel from the Earth surface into space and then have the fuel depots there. And there is some benefit to doing that even that way. But just imagine if the fuel depots in space could be fueled entirely by resources from space. That's the point, right? So that is the future that we're looking to create first. And then once we have that refueling capability in space, we can go to Mars, asteroids, go to the moon, bring stuff back to Earth, all that sort of stuff, okay? And that's really what it is. So, I guess the purpose of this is just to remind you that it's been done before. Of course, not the resource extraction part, but even, we actually have brought materials back from asteroids. We brought a tiny bit of dust back from Itokawa on Hayabusa. And although they would have liked to have gotten more, even governments, as expensive as they are and not focused on optimizing for cost, have been able to go to asteroids. There's a great asteroid mission out there right now, Dawn, of course. And we're going to drop the cost of being able to explore asteroids by a factor of 100, ultimately. Okay, so I told you about Peter Diamandis and myself. When we started this company, we didn't have to look very far to find our chief engineer, Chris Lewicki, somebody who's well known to the Space Frontier Foundation community. He was the SEDS global chair for a long time. I've known him for 20 years also. He's an aerospace engineer. He landed the last couple of spacecraft on Mars as the mission manager at JPL. He was working at JPL for 13 years. You know, he could have ended up as the director there someday. And he really has been great. He joined us a couple years ago and brought with him a few of the key people involved with all those programs. So I actually got a call from JPL saying, hey, why are you hiring all our best guys? And I said, I'm sorry, you know, maybe we can work together someday. But the fact of the matter is we've had to bring together some really great people, and we've gone out to industry as well. We've brought people to work with us from industries like chip manufacturing and, of course, software and all that stuff. So we've really pulled together a great team of people. We have about 35 people now. We're going to grow that up to about 50 or 60 in the near term. And we're going to begin to manufacture these ARCID spacecraft on an assembly line, like they're just printing them out the way it should be done. It shouldn't be surgery every time you make a spacecraft. You know, it should be like, the percentage of its cost that is attributable to its materials should be the majority and not the time eventually. Anyway, so also one of the cool things about kicking this company off was we got to go and talk to some of our friends. Peter and I have known a lot of these guys who have invested with us through different ventures. Charles Simoni, of course, was the chief architect of Microsoft, the guy who invented Microsoft Word, and he went to space twice on the Soyuz through Space Adventures. And when I talked to him about this, he said, wow, that's awesome. I love that. I'm in. And we talked to Eric Schmidt from Google and Larry. And Eric said, hey, I think that's really great. This needs to be done. And every time we talked to Larry Page, Peter had a meeting with Larry Page the other day. He said, you know, guys aren't thinking big enough. You really need to go after bigger asteroids and go way out further. So he's just, you know, for this is just barely cool enough for him. So, anyway, he wants to go beyond the solar system. So the fact is that we also struck a nerve with investors, okay? So having been an entrepreneur for 15 years and had mixed experiences trying to raise money, the early days of Space Adventures were tough. We were selling space flights with the Russians and doing zero-G and stuff like that. And we didn't have like some unique technology or some shiny object that investors would like. And we did find investors, and we have some great investors there, but it was tougher. Not for Planetary Resources. It's a big idea. You know, people, I tell them, you may lose all your money. You know, we may figure a bunch of stuff out, and then we may fail in some way, and it's a risk. They said, that's all right, we understand. We don't care. This is what life's all about. We want to live in a world where humanity is really exploring space and going into space sustainably and in a way that can not be influenced ultimately by what governments are doing. So it's not dependent on the budget or the recession or things like that. And so we've been very, very honored to have some just absolutely fantastic people as investors. We brought on a few more, actually, since the announcement, and some other big names, and at some point here in the next month or two, we'll put out a press release about that, but people every bit as well-known and committed as the folks you see on this stage, on this slide right here. Same with our advisory board. You know, I won't go into all these people. You recognize a lot of names here, but just from different industries, you know, Joint Chiefs of Staff, you know, famous movie producer, different folks, planetary science, all that sort of stuff. And we've really just been trying to attract the best of the best to help us out. These guys are all actively involved. Tom Jones, many of you know, astronaut, brilliant guy, planetary scientist. Been thinking about asteroids for a long time, flew in space 4 times. He's been brilliant. He was at our public announcement, very supportive. So let's talk about our approach a little bit. You know, right now, you saw in those previous charts that it costs about, let's say, a few $100 million for the government to send a mission to an asteroid. Well, that's just not sustainable. You can't, for a commercial enterprise, you can't spend hundreds of millions of dollars every time you want to go put a camera near something that you might want to mine. So we've got to build spacecraft that are an order of magnitude at first, and then 2 orders of magnitude cheaper. Ultimately, our goal for the ARCID line is to literally build spacecraft that are $1 million a copy. Okay? Now, the components on a lot of these spacecraft are more than $1 million a copy right now. You've got from, you know, reaction control wheels to the star trackers to the propulsion system to all the custom-written software and everything else. It's just not a assembly line yet. The components are too big, too expensive. And so we have to start to hit those down one by one. But ultimately, we are going to leverage exponentially growing technologies, bring commercial off-the-shelf stuff into it. You know, when NASA does something, and I don't want to just sit here and bash NASA because NASA's great and NASA's done some great things, of course. But we all know that, you know, if NASA's going to fly a mission to Mars, they have to go back 15 years to the last processor on the 386 board that was space qualified. And whereas a commercial company can take the i7 chip, actually we hired one of the guys from Intel who was on the i5, the lead guy on the i5 chip, and just plop it into the spacecraft. You know, if something else comes out a couple months before, we can run a few tests and put that in. And so it's just completely different mindset. We can take the risk that government, unfortunately, has lost its ability to take over the last few decades. And that will result in a radical reduction in spacecraft cost. So we're very excited about that. What are we doing different? Again, these are much of the same things that I've spoken about, vertically integrating our development. And, you know, I really have just an incredible amount of respect for SpaceX. Steve Jurvetson's here at the front table as a board member or an investor in SpaceX, and Elon's a good friend. And, you know, Elon, we talked about this a couple weeks ago, and I was asking him about vertical integration. He says it's not like particularly religious about it. It's just that you can't be slave to a subcontractor that's going to charge you $1 million for a part that should only, you know, that only gets built once a year or twice a year for 2 customers. And therefore, it's absurdly expensive, and then you have no control over the price and whether you can even get it on time. And it's just the aerospace industry, the traditional defense and aerospace industry, is filled with parts and components and subcontractors that are used to doing business that way. And so if an industry develops where all these components are widely available, great, you know, but in the absence of that, we're going to have to do a lot of this stuff ourselves and try to make those things available to other companies as well. There's nothing about that would prevent us from doing that. But there'll be a lot of innovations that come on a component level for deep space spacecraft. Right now, it's been surgery to build one, and it shouldn't be. So ultimately, the 4th bullet is really the important one, which is that we want to build asteroid exploration capability at less than 1% of the historical cost. That's super hard, but we will do it, and it's going to take some time. Okay. These are what the ARCIDs look like, at least early versions of the design. It's evolved a little bit. But the 100 series is without deep space prop and comm. We use those in low Earth orbit. It's a test bed, and it's also for learning more about particular targets that we might go after. The 200 series would be missions that are nearer to the Earth, and the 300 series has a full a capability to talk over 20 million miles, for example. So you got deep space comm and deep space propulsion. Now, you guys who are spacecraft engineers know that comm is a really tough one, and we have to really innovate there. I mean, we're looking at things like laser communications, ultimately, because if you're not using optical comm, you're using radio, you have a big antenna, you have a big spacecraft, the cost goes up, the whole thing, you know, you remember the Voyager, it's just like a big dish and an antenna, that's it. You know, so if you are going to be communicating over tens of millions of miles and have any sort of decent data rate, you've got to be able to do that, and have any sort of reasonable cost, you've got to be able to do that using optical communications. Of course that, well anyway, we can talk more about that. So this is sort of just an infographic of how the exploration of the inner solar system and the asteroids could evolve. You know, we're going to, the other thing I didn't mention, but I'll mention now, if you look in this middle line here, is that we're going to be sending swarms of spacecraft. So we early on figured out that it's not a good idea just to send one, because if you send one, if it fails, your mission fails, okay? Just like distributed computing. If you have 5 computers and there's a failure rate, even if you have a failure rate of 10%, okay, per unit, the mission success rate, if the mission can be successful with 2, for example, is still 99.x% if you've got that because of the law of permutation. And it just, the chances that all those spacecraft fail go exponentially down. So anyway, it's the failure rate for a particular spacecraft probably not going to be 10%, but the point is that if you do it with more than one and you look at the kind of failure modes that are out there and things like that, it just makes a lot more sense. You can cover a lot more ground, gather a lot more data, do it a lot less expensively, and have these guys communicate through near field communications and things like that. So that's really cool. Okay, so here's an idea of what this might look like. Brian is a great artist. I don't know if he's here, but he does a great job with these sorts of images. This one does not have the solar collector, so this would be powered by nuclear. That won't happen for a while, so it should have a solar collector on it. But you can see the mining of the metals on the left, and then the oxygen and hydrogen on the right over there. So what's happened recently? A couple of weeks ago, I was at the Farnborough Air Show with Richard Branson, and we announced that we would be an early customer for Launcher 1, which is the satellite launch capability being developed by Virgin Galactic. They came to us and asked if we'd be interested in that, and we said absolutely. It's, their goal is to get the cost of launch to below $10 million per launch, down to for a 500-pound spacecraft into LEO. And so we could actually pack a couple of these small Archids on that with enough propulsion to get out into deep space on their own, potentially. Pretty interesting. But that's not going to be around for another 3 or 4 years, so we'll be launching on other vehicles before then. But we've also been busy in the customer and strategic partner realm. Nothing that I'll talk about right now, but lots of people out there, lots of people who are interested, and we've signed a couple of agreements there. For those of you who are following us on the website, we have been pretty active in crowdsourcing and public engagement. That's kind of been a goal of mine and Peter's since the beginning. And Peter's really been doing a lot of that work, but we've got emails that go out and we ask people for comments, and we're exploring. For example, we're building these Archid 100s to send to space, into LEO, again, as test beds and as observation platforms. And we may make part of a satellite or an additional one available to the crowd for use for taking pictures or looking at deep space and all that sort of stuff. And so we're looking at some of that. We really want to keep public engagement high. Ultimately, this is a company that we want millions of people to be behind as we really try to move the needle for humanity. You guys, I'm sure most of you heard about the B612 Foundation unveiling. I think that's a great project. We're certainly talking very closely to those guys, and I'd love to see that thing get funded. That's really something NASA should do, I think. I mean, to have a map of the inner solar system, the fact that we don't have that now is ridiculous, and we really, really should do that. Okay, so here's a slide of the different ways you can reach us. I'll probably come back to this. I think this might be the last one, but I'll show you the video first, then I'll leave it on the slide so you can write that down while I'm answering questions. So let's just see. Do I have any more video here? We're going to change the way the world thinks about that. No, I think that's it. Okay. All right. So let me come back to this, and we do have a video of our sort of our corporate. Hang on, can somebody come up here and help me put this? Here you go. Thanks. It's not my computer, so we do have a great video that we showed at our initial press conference. It's on YouTube. I encourage you to go watch that. It's got some interviews with different folks, and just go to the slide that has the contacts. So anyway, I think we have some time for questions. We're supposed to wrap up by 10 till 2 or something like that. So yeah, we've got about 10 minutes or so for questions. So fire away. Purple shirt.
Got a question. About 2 or 3 years ago, I sort of went through a mental process with some other people about what is the best way to open up the solar system, moon first or asteroids and whatnot. We sort of settled on moon first, but I was very impressed, quite honestly, by the logic behind Planetary Resources plan. To what extent did you guys go through really comparing asteroid versus lunar resources, especially now that we have the new moon with volatiles at the poles? To what extent did you go through and consider all the factors, deep space, communication would be easier to the moon? 1/6 gravity, I think, would actually be a positive for the moon for processing, but for transportation, obviously, asteroids has the advantage. To what extent did you guys really go through that process? We
went extensively through that process, and so first I'd like to say that I think, the moon is great. I would like to go there myself. We at Space Adventures have been working on a circumlunar flight for some time. I think the moon is fantastic. Okay, we should have bases on the moon. However, I think that at the end of the day, you stack everything up and you look at what's in the lunar regolith and even on the poles and all this sort of thing. If you're going to have resources available in space for use in space or ultimately potentially back on Earth, you really don't want to have to go into the gravity well of the moon. So I think for those, if you're going to use resources on the moon, great. And I would encourage as much lunar development as possible. But if you're going to use them in space, you want them available in deep space, or to bring back to Earth, I think it does make more sense to take advantage of the near-Earth asteroids. I think the processing question also, we've thought a lot about that, and I think processing in zero gravity presents some interesting opportunities, actually. And I think it's not going to be as difficult as one might imagine, which has to be done differently. But heated up fluids and the zero gravity environment can be used to our advantage. So, again, I love the moon, though. I don't want to sit here and say bad things about the moon because I think the moon is great. But I think for exploring deep space and getting those resources available, you want to use the asteroids. Question here.
Two very specific questions. You have the 9-inch telescope. If you're looking for a 100-meter asteroid, how far can you see? How close does it have to be? And the second is, what kind of data rates do you think you can get with the laser comm?
Okay, so two great questions. So first of all, we haven't actually decided yet on the optic for the Arcid 100. So it may be substantially bigger than that. So it's too early to answer your question on that. Second, in terms of laser comm, you don't get a huge data rate from deep space, but you don't need a huge data rate if you have a lot of intelligence in the system out there. And so that's another area that we're working on, and we have another contract that'll be announced here sometime shortly with another partner working on spacecraft intelligence and things like that. So you don't want to have to send back lots of images that are similar and do the processing here if you could just do the processing there and send back the right one, so to speak. And we're looking at lots of ways to optimize the value of data that comes through those pipes. But we do know that, and by the way, I don't, when I say low data rate, it will be fine. I just mean that, it's not like you're going to get a gigabit per second or something absurd like that coming out of deep space using optical comm. Pointing is really tough. So I don't want to go through the technical specs now. We're still looking at that. But, okay, question.
So you talk about all the, the value of these platinum group metals, and that, in all of history, you've, you can from one asteroid get more than we've mined. So obviously that makes sense. You bring back an asteroid, now we have tons of it. Is the economy going to support that? Is it, have people figured out ways to design around the, the lack of availability of these materials? Fundamentally, how will that market change when you bring back tons of it?
So that's a great question, and some of the naysayers to asteroid mining have said, well, gee, if you bring back all the platinum, then the price will crash. And I say, great, I would love to see that. I would like to see a world of abundance. And you need not go back further than about 160 years ago into the mid-1800s when you learn the story of aluminum. So for those of you who know that story, aluminum is a very prevalent element in our Earth. But we did not know at that time how to separate it from its oxides, okay? And so if you were to have gone to the court of Napoleon in the mid-18th century, the mid-19th century, and you were, for example, the king of Siam, they would serve your food on aluminum plates because it was the rarest. And the next most important people would get the gold and the silver and all that sort of stuff. Then we figured out, hey, we can separate this from its oxides, and now we know how to do stuff. And now look, we're aluminum. We use it everywhere. Airplanes, automobiles, everything. And so that's what happens when the price comes down and it becomes abundant. The platinum group metals are very useful metals, just as an example. And the fact that they are not abundant means that they are not being adequately used. But if you look all over, look it up, renewable energy, medical devices, all sorts of stuff. Those are really, really important metals. So I hope we crash the price. Next question back there.
Yes, you were talking about using laser comms. Oh, sorry. You were talking about using laser comms, and one thing that I wonder about is most of the time when you have radio communications on a spacecraft, you're also using that radio communications for navigation. And have you looked any at how that's going to play out with how you're actually going to figure out where the spacecraft is? And
We're looking at all that stuff right now.
Okay.
Again, the guys we have working on this are really just incredible. And we have all sorts of creative solutions you'll hear about someday. Question here, the young lady.
Hi, I'm the project manager for the Teachers in Space program, and so I'm always looking for ways that we can get the latest, coolest stuff and put it into the hands of teachers. Have you considered yet whether there are aspects of what you're doing that can easily be packaged and given to teachers for their students? Some aspect of the science that you're doing?
That's a great question. Absolutely. And so one of the things that we're doing, and I have to give the credit to Peter Diamandis for really kind of getting this started. If you go to our blog, you will see that there's been some discussion about maybe opening up a Kickstarter campaign, and not because we need it, but just to engage into the public persona and get more people involved in space. We really decided that we wanted to have massive public involvement. And so while we have our own satellites that we're building and launching, the idea was, would we make part of one, or maybe even build an extra one to become available for use by educational teachers, students, people who want to take a picture of their house, whatever. And so there are we're just figuring all that out now, but we are trying to find ways to always have public engagement, particularly with teachers and students working on and having access to some of the assets that we have. We have even some interns. So in Seattle, there's actually a really cool high school system, and they're sort of like domain-specific high schools. So there's an aviation and space high school next to the Seattle Museum of Flight. And so this summer, we had a few of those kids come over for like a 2-month internship, and they did awesome. These are like 15, 16-year-old kids who've been learning about aviation and space in high school, and they're really doing some interesting stuff. So that's a big focus for ours. We're going to try to do more and more of that as time goes on. So maybe like 2 more questions, and then we'll wrap it up. Right here.
Yeah, I was just wondering, I see the little trend on the actual mining procedures there, and I'm just wondering, mining takes a lot of water. I'm seeing, on the slide that these things are being returned to Earth or returned to the moon. And then I know the Keck Observatory paper talked about actually capturing the asteroids and returning them. So what is the actual mining process that you're going to use?
So we've thought about that a lot. Okay, we have a couple people who are working on just that. We have scoured every paper and every historical analysis of anything that's ever looked at this sort of thing. We've added some new concepts to it. We're talking to people in the mining industry. But that's down the road. I don't want to give any false impression. Right now, we're focused on gathering data. There are a lot of hard problems to solve in terms of reducing the cost of spacecraft. I'd love to spend all my time thinking about that problem, but it's not a good use of my time right now. So we have thought about it. We have a couple people who are working on it, but not to a point where we can talk about it publicly. Okay, last question in the blue shirt here.
2 short questions. One is, you talked about fuel depot. What's your thinking about building your spacecraft on orbit? And then the second one, for the new generation, what kind of degrees should they be pursuing in order to be hired as asteroid miners?
Well, let me just answer the last one. I didn't quite hear the first part of the first question. But what kind of education should people be pursuing to be asteroid miners? Wow, this is near and dear to my heart. STEM, science, technology, engineering, mathematics. This country, we need to do more of that. And you should go out there, and we actually, there was a quote on that slide that I showed before about somebody saying that they wanted to go out and study science and engineering now because of this potential. And I've seen that across some of the other really cool companies in the NewSpace industry. And so that's what it is. China, God bless the Chinese too. They need to go into space, and I wish them all the success because we're one planet and we need to go to space. But they're graduating more engineers than we graduate students every year. And so we have to have more scientists, engineers, mathematicians, technologists. That's what they should study. All right.
My first question was, how would you build your spacecraft in space instead of building it on Earth?
How will we?
Yeah, or are you thinking about it, and what are...
it depends on which spacecraft. So the Arcid series we're going to build on Earth, because these are small 25 to 50 kilogram dry mass probes. They're observation platforms. And then again, you know, we have thoughts on the next series, the ones that are going to start to do actual resource manipulation and things like that. But we're not spending a lot of time on that right now. So of course, in-space manufacturing, when it's feasible, and certainly fueling is something that we would look at very seriously. So, okay, I don't want to be the guy who makes us late. So it's now 10 till 2. I was supposed to be, wrapped up by this time, but look, it's always a great pleasure coming to SFF conference. It's great that you guys come to this. Keep coming every year. It's great to see so many young people here. I'm sure I'll see you again in the future, and we'll have a lot more exciting stuff to talk about. So thanks, everybody.